Therese, can you hear me? If you
I can,
do
yeah.
a thumbs up because we can't hear you yet.
Yes, can you hear me now?
I think you can hear me. Now we just have to be able to hear you.
Can you hear me?
What it's like to be married to a man.
Okay, we heard that. But that was you in the back?
That was.
Oh, heavens. I thought we'd fixed our speaker problem.
That's where I'm at. Just right.
Heavens.
Can you hear me now?
Therese, I'm going to log off and log back on again.
Okay.
Oh, never mind. We just heard you.
Do it.
All right. Yeah, that's fantastic. Amazing. So, all right, we have it figured out. I'm going to share my screen. And okay. Welcome everyone to Chemistry 131. I'm Dr. Musk. I'll be your host for this journey into organic and biological chemistry, which is an awful lot to cover in a 1-quarter class. So there are different kinds of courses. There are survey courses where we learn a little about a lot of things. And then there are normally like later on more in-depth courses where we learn a lot about a couple of things. This is definitely one of the former. We learn a little about a lot of different things. All right. My PhD is in chemical biology, which is mostly, for me anyway, organic chemistry. So I studied for 5.5 years after undergrad. That was mostly studies in just organic chemistry. And we have 1 quarter to like learn some of that and some biochemistry at the same time. So we're not going to learn everything that I learned over those 5.5 years in half of a quarter worth of time, but we do get to learn some first principles that will aid you as you encounter organic chemistry in your real life. And if you study it more, you'll have a good basis to start from, at least. All right, that's what I'm hoping for you. So where do we start? Probably by getting to know you guys' names. So let's call roll really quick. And for those of you who are in class, I would also like you, because I am getting old enough where I have some trouble remembering everybody's name. Go ahead and fold that piece of paper in half and put your name and whatever pronouns you are most comfortable with on that so that I can remember who you are. And I have some markers, so just pass those around as you finish it. Okay, so let me call roll really quickly. Billy Champignon. Billy, did you know your last name means mushroom? Yeah, I used to look like one too. Oh, that's awesome. I only know that because I really like mushroom identification and mushroom hunting. It's like one of my nerdy things that I like to do. So Asacia Cofield. Asacia?
Yeah.
Hi, Asacia. Did I pronounce that correctly?
Yes.
Awesome. I love that name.
Thank you.
Faith Crawford. I think. Haley Green. Hi, Haley. Therese Hansen. Therese is online with us, I think. Therese, you still there?
Yep.
Awesome.
I'm here.
McKenna, I think I saw. Yes. Rebecca Jaffe, I think I saw. Nicole Marley. Hi, Nicole. Aaron Meek. I actually had a really good friend in high school named Aaron Ray, so it's going to like confuse me a little. Yeah, yeah. Now she's gone off the deep end a little bit. She's like an ultra marathoner, and like people that do that like really don't do anything else because I think it takes like constant training to be able to run ultra marathons. Yeah. But people that are in that good a shape also tend to have like weird physical adaptations. So she's had 2 kids and like she literally had like 20-minute labor and delivery for each one of them. Her body is just like done.
It's cool. Then you guys don't say I'm a big brother, but no.
Yeah, yeah. So anyway, like I guess if you want to have a really quick labor and delivery, be an ultra marathoner because the adaptations make your body just like done. Yaseli, is Yaseli here? I think Yaseli was going to log on as well. I sent, I think. Okay, I guess not. That's fine. Mia Perez. Hi, Mia. Veronica Repperger. That's awesome. I've never heard that last name before, but I love it. Brittany Shepard. Brittany is not here. Aiden Vandervoort. Aiden is not here. Okay. And that's with our customary, like, wait an extra 5 minutes on the first day of class so that people can find their way. Maybe they didn't like log on to the course camp site and realize that we're upstairs instead of downstairs for lab, but hopefully they'll figure that out pretty quickly when they go down there and nobody's there. Awesome. Okay, so next thing that we have to do is we have to check out our course Canvas page so you know where everything is. One thing that I've not yet done, well, actually with 131, I think I might be finished with all this. I think I have all of our due dates for the entire course plugged in to Canvas already. If that is not the case, that will be fixed very, very soon. One of the things that I struggle with is like jobs that are pure drudgery. You know what I mean? Like just inputting data. I can only do so much of that at a time. So for the first like week of the quarter, I have to like take short shifts of like 45 minutes of hardcore data entry, like changing due dates and things like that. If I do it all at once, my brain will explode. So if they're not all there right now, they will be very soon. Now, what will the course look like when you log in? It's probably better for us to look at it in student view instead. So important links for the course. We should have a link for office hours and also a picture of what your textbook looks like. All right. I will add a link because at least one of us is going to have to be joining via Zoom for the lectures. So I'll have another Zoom link for lectures here. The office hours link has to be different because I use that office hours link for all my classes, not just for 131. So I have to give the same one to everybody. All right. And for other reasons, it doesn't make sense to use the same Zoom link for all of your different classes. Does anybody not have a textbook yet? You want to borrow one for free for the quarter?
Yes.
All right.
Same.
I promised one to somebody, so I have at least one to lend. The cool thing is they're really, really cheap. Doesn't matter which edition you get. Any of the old editions of the book are perfectly fine. As long as it's general, organic, and biological chemistry by Smith, it'll work for this class. All right. Why, hello. In half, name and pronouns, please. We're not going to spend very much time on the course syllabus because that's drudgery and I hate drudgery, as you guys already know, but we're going to look at it to just point out a couple of things really quickly.
It's not linked under the syllabus. This is linked under your other.
You shouldn't even be able to see this here. Why can you see that?
So
I hid that. Why
I
can you see that
all
now?
of it, but when.
All right, all right. Well, I'm gonna refix that because that drives me
Yeah.
absolutely batty. So yeah, I interactively hid that and somehow,
All those, like on the left, those things.
yeah, you shouldn't be able to see most of this.
Yeah.
So anyway, ignore that syllabus tab because it's going to go away. All right. Everything that you should be able to use to complete the course should be right in the modules on the front page. All right, in those boxes on the front page. That's really irritating because it took me a while to figure out how to hide the stuff over here. And I think that when I copied over my old Canvas course where everything was hidden, it undid those settings and unhid that stuff, which is why copy a Canvas course if you undo the work that I did. All right. So anyway, here is our course syllabus. I'm pointing out just a couple of things because all of you are capable of reading. All right. First of all, right here at the top of the syllabus under my contact information is my real cell phone number. All right. I don't have a burner phone just to receive texts from students. So you can use that anytime that you need to contact me as long as it's a reasonable hour. Should that be like the first place you send a text if you're struggling with a homework question and haven't thought about it for very long? Probably not, but I do want you to be able to get in touch with me if you're having difficulties in the course. All right. So you have that number. Feel free to use it. I also have lots of office hours this quarter that I'm really excited about. The reason I'm really excited is because it was really hard for me to find office hours last quarter because I was teaching on both campuses. On Mondays and Wednesdays, I taught in the morning here and then in the afternoon at Mount Vernon, which basically like burned any chance of having any free time those days at all. So I feel like I'm free again and we can have plenty of time to interact with one another. So Monday through Thursday, the 11 o'clock hour I have available, and then Tuesday, Thursday, 4 to 4:50. So that sort of works pretty well for you guys, the 11 to 11:50 hour, because it's like right before this class. But if neither of those times work for you, does that mean that you cannot meet with me for office hours? No. All that means is I know that those 6 hours I'm going to have available and I don't have meetings scheduled over the quarter. All right. We can work out a time where you can get extra help from me. You just have to let me know that you need it and we can work with our schedules and schedule a different time if none of those times work for you. All right. The third edition of the Smith textbook is the one that I have listed with the library as my textbook for the course, which at this point is like 2 editions old. I'm doing that because I don't want you to spend a lot of money on it. All right. I have seen that textbook available for purchase, not for rent, on Amazon for like 15 bucks. So don't spend a lot of money. If you can find the 4th edition or the 2nd edition or the 5th edition for cheap, just get it. All right. Doesn't really matter which one you have because we're going to use a little bit of a workaround to do our homework for the class, which is from the 3rd edition of the textbook. I just PDF copied the problem pages so that all of us can use the same edition of the textbook when we do our homework. All right, just because the numbers and exact problems change a little bit from edition to edition.
Right, and so this is the one that you had given the link for last year. That you had.
That doesn't exist anymore. Yes.
Right, okay, but you could download it though, right?
No, it does. The literal link is dead.
The literal link is.
Yeah,
dead.
it's
I
dead.
did check that, but then it's not, but you were able to, was one able to download it back in the?
Yes,
Okay, then. I
you
did
were.
that. Okay, good.
It was possible to do that as a precursor to actually purchasing the textbook. I have to say that loudly.
I have that, if anybody wants the PDF of the text.
As a precursor to actually purchasing the textbook.
Right, of course.
I'm required to say that legally.
Guys.
For a short evaluation period, it is legal to evaluate a PDF of the textbook. But
Says
that
the
has to be
Danish
followed
government now,
legally
that website.
by purchasing the textbook. Yes. Okay, so another thing that I want to point out, just because it's an idiosyncrasy that I have as a professor compared to others, I hate the grade A- with a passion, mostly because I got a couple of A- in college that were the difference between me graduating magna and summa cum laude. I wanted summa, I got magna because of a couple of A- and a public speaking class with a professor that had a little vendetta against me and gave me a B+, even though I had over 100% for the course. So I don't know how that's possible. And then back then they weren't as concerned about like responding to student complaints as they are now. The student as customer like motif had not taken hold in college yet. So after my professor gave me my B+, she vanished for like 2 months off the face of the earth, and I wasn't ever able to get that rectified. So those things were, anyway, I hate the grade A-, so I tend to not give them in my classes. The only time you would ever possibly get an A- in the class is if you're like right at that 90% cutoff, or maybe like a hair below, and you probably really deserve a B+, but you're close enough that that doesn't make sense either. I try to avoid giving A- if at all possible, which means if you're over 90% significantly for the class, you're getting an A. All right. It's hard enough to do that. You can read about how the grade is going to be portioned out. It's a pretty standard breakdown. I do want to note that about almost half the grade for the course, 45% of the course grade, are what I consider to be more effort points than summative kinds of evaluations. So in education circles, we talk about formative evaluation and summative evaluation. Formative evaluation are things that are supposed to teach us and help us improve. All right, so things like homework are types of formative evaluations. Like I can look at how you're doing, respond with feedback, and help you get better. I regard labs to be the same thing. Pre-lab quizzes to be the same kinds of thing. Basically, all the evaluations in the course, other than the exams, I think of those as formative evaluations. That's 45% of your course grade. Those are effort points. All right. So if you get a perfect 45% out of 45% for your effort points, then you really don't have to do that well on the exams to end up with at least a B in the course. So think about that as you're going through the course, because exams aren't easy, especially in an organic and biochemistry course. So get the easy points while they're available to you. And then if you end up with a C on an exam or even a D on an exam, you're still going to have a route to getting a decent grade in the course. All right.
So for the exams, I know last spring quarter, we offered the correcting mistakes on it.
We'll talk about that.
Okay.
I still do that.
Okay.
All right. So I do offer curves as part of my grading scheme for exams, but I don't give those away for free. We'll talk about that once the first exam is in the books. All right. Other than that, like, be a kind human being in class, come prepared to class, complete pre-lab quizzes before you go to lab. Those quizzes are not up on Canvas yet, but they will be, and they're going to be completed as Canvas quizzes. They will close for you to be able to get points for them, like when the lab that goes along with that pre-lab quiz starts. Make sure that you read the lab and do the pre-lab quiz. It's like going to be 3 questions or something for each one. All right, that's 5% of your course grade. Just effort points. Take the time, read the labs, get those points. That is going to ensure that you come to lab prepared, which is really important because we only have 2 hours for lab. If I was designing the curriculum from the ground up, I would have insisted that we have 3 hours for lab for this course, because really, like, some of the labs, we need that long, especially for the experiments that are organic chemistry things. We have to like jump through hoops as faculty members to try and come up with an organic chemistry lab that fits into 2 hours. If you're in a majors level organic chemistry class, you know how long the labs are on average at university? How many? 4 hours. Yeah. Sometimes it's hard to get finished with your lab in 4 hours as an organic chemist.
Organic, like all night. Yeah, horrible.
Yeah. At my old job where I was teaching majors level organic chemistry, the only time we could actually schedule that lab was from 6 to 10 p.m. on Thursday nights. That was like the only time when none of the student athletes had practice and everybody was available for a 4-hour block of time. If you schedule at any other time, it literally destroys a student's ability to schedule anything else for the quarter. So we don't have that problem, and it's a non-majors class, so we shouldn't really need 4 hours. But 3 would be really nice. 2 is not enough, which means we have to hit the ground like hauling butt to be able to get labs finished in this class sometimes. All right. So the pre-lab quizzes will ensure that you've thought about the safety hazards, and we don't have to spend time talking about that at the beginning of lab, and that you've read through the lab procedures so you sort of understand what you're going to be doing for the week. All right. It's really important. The next link after the syllabus in that introductory module is the course schedule. So I should have all of the homework and lab due dates baked into this course schedule. They're also input into Canvas, which means that your Canvas course calendar will remind you when you have an assignment due. That's really nice for not forgetting to turn in assignments on time. All right. How will you actually turn in assignments? For the most part, we will turn in assignments as PDF files. So this is one part of like the pandemic that actually took root in my classes, and I think it's a better procedure than turning in paper copies of things. If you have your own paper copy and you scan that copy and submit it as a PDF, there is no opportunity for germ transfer then. All right. So I don't get germs from 60 students over the course of the quarter every time that they turn in their 60 assignments twice a week. And that's a huge improvement. So let me give you an example of how that might work. When you go to turn in your first lab, you will scroll down past the content videos. So these content videos are going to help you get ready for the time that we're in class together talking through these things. I try to teach my classes as much as possible in what's called a flipped classroom approach, which means that you're going to be spending your time learning lecture more at home than here. And while we're in here, we're going to be talking through the hardest parts of the material. All right. So after teaching this class for like 5 years, I tend to know where people are going to have problems on exams. I want to spend as much of our class time together focusing on problem spots instead of the stuff that's easy and the stuff that's hard. The stuff that's easy, you can learn by yourself. And I have prepared short topical videos over the material to help you learn that easy stuff. And when we get together in class, we're going to spend our time talking through the stuff that's not as easy. So let's back up and talk about how we're going to turn in homework or labs. So in this lab activities module, here is our lab for the first week of class. Our first lab, which will actually happen next Tuesday. All right. If we click there, and I've already noticed that somehow the due dates did not migrate the way they were supposed to. So I've got to fix that. All right, that's totally fine. The due dates will be fixed very soon. They are on the course schedule already, and they will be migrated in so that Canvas's calendar will give you reminders. So when you go to turn in this assignment, you will print out a copy of your lab and bring it with you to lab. You will complete the lab on that copy. And then after that, you will use whatever app you're most comfortable with on your phone to scan and make a PDF of all the pages of that lab. The app that I think is the easiest to use is an app called Genius Scan, 2 words. All right. The reason I like that one is because it is not obtrusive. It doesn't have a ton of ads. There are other ones like Cam Scanner that have ads and maybe malware. All right. Genius Scan is a good app, and it's available for both Android phones and iPhones. There is also a way using an iPhone's native camera app to turn your photos into a PDF as well. I don't use an iPhone and I don't understand their programs very well, so I can't teach you how to do that. But Genius Scan works for everybody. So that's the app that I recommend. If you're having problems taking your pages of a lab or a homework assignment, scanning them and making a PDF, come by office hours and we'll figure out a way to do that works for you. All right. Most people, after surviving education during the pandemic, have learned how to do that at some point. So one thing that I will ask is whatever app you use, please turn all of the pages of your assignment into one PDF file, not a PDF file for each separate page of your assignment. That will make it much, much easier for me to grade those. And the reason why is because when I go to grade those PDFs, I open them up in the instructor version of Canvas, and it essentially lets me grade them on an iPad, essentially the same way as if I were grading a paper copy of the assignment. The benefit is no germ transfer. And also, as soon as I'm done grading your assignment and enter a grade for it, the grade comes directly to you via your Canvas app. And also, you can look at your feedback instantly. You don't have to wait for me to hand back an assignment in class. It's just a better system. So if I were to click start assignment, I can pick wherever that PDF file is on my phone or on my computer if you send it to a computer through email or something like that. And then you can submit the assignment. Most people use the Canvas app on their phone, find the file, and submit it right from their phone.
On the Genius app, you can actually submit it through Genius. Like if you go to export, it'll go Canvas and you just select the course, highlight the homework, and then it sends for you. We don't even.
I didn't know that.
Yeah,
That's
it's a
awesome.
deal.
That's even more streamlined. Yeah, I love anything that makes stuff easier like that.
Yeah.
Because like working with files is drudgery, and anything that I can do to avoid time doing drudgery, I want to like rescue those hours of my life.
Yeah.
So yes, that is awesome. Now I have to learn how to do it so that I can like throw instructions for that into.
It's just the export button, and then you just pick other apps, and then Canvas, and then boom.
Fabulous. Love that.
Yeah.
Okay, so now we know how to submit labs or to submit homework assignments. Your homework assignments, I do low tech for our homework assignments. One, because most of the educational apps on the web that have homework assignments for organic and biochemistry courses, their homework isn't tailored to non-majors. It's tailored to people who are majors in organic chemistry or biochemistry. So finding problems of an appropriate difficulty level in their problem banks is hard. Most people haven't got good homework apps for non-majors, organic and biochemistry. So we're just going to go old school and use back of the chapter problems. All right, so this homework will probably remind you of homework that you did in a class 20 years ago. All right, which for some of you might be preschool or like when you weren't born yet. And that's fine. Any questions about how the course is going to be run, generally speaking? Let's talk a little bit more about that flipped classroom approach. So what would class and what would homework look like? All right, homework for us partially is going to be completing labs and back of the chapter problems. All right, homework assignments. But the other things that we're going to be doing when we're at home we'll be preparing for class by watching topical videos. So the first chapter from the Smith textbook that we're going to be covering for organic chemistry is chapter 11. Before we even start talking about chapter 11, we may talk a little bit about it today, but we're not really scheduled to, all right? Before we even talk about chapter 11, you at home can watch topical videos that cover most of the material that's in chapter 11. All right, really all the material that I think is important from chapter 11, but maybe not at the level of difficulty that would allow you to get an A on the test if you just watched the topical videos. So these topical videos are by and large pretty short. I try and keep them to between 5 and 10 minutes long at the longest. Every once in a while, there's a topic which is like a little bit longer than that, and I apologize in advance. Why? Okay. A lot of professors that host videos use Canvas's hosting tool called Panopto. Panopto sucks. I'm not going to get into the weeds of why it sucks, but for the same reason that I looked for deadlines for all of my labs and they were just gone. Whenever we migrate a course to a new version, like if I copy an old Canvas course and then like make that my new Canvas course and change it for the new quarter, Panopto's like video permissions just go away and then students aren't able to access videos. So instead, I just host all my videos on YouTube because YouTube will be around until Armageddon hits, right? So if YouTube loses the ability to show videos, then we have bigger problems than this course. So you can see this one is a particularly long video at almost 12 minutes. Most of them are shorter than that. And this one just covers the first couple of sections within chapter 11. If we move on to the next one, you can see we've got a couple more sections, and I'm going to go back so that we can look. After those first couple of videos, there is also a short reading quiz. All right. These reading quizzes are little self-checks. to make sure that you're thinking through the things that you should be from those videos as you're watching them. All right. You can independently read your textbook through those sections, watch those topical videos, and then this is a self-check to make sure that you're understanding things the way that you should be. All right. I'll add deadlines for those reading quizzes because that deadline went away as well. I have no idea where all the deadlines went. I spent like 45 minutes putting them all in. That's really frustrating. But those deadlines will help us keep pace with the class so that you're not going to be trying to cram through the material for 4 chapters the night before the exam. All right. That is an incredibly poor strategy. I will not lie and say that I've never used that strategy, but for most students, it doesn't work very well. And even more so for most students, if you try and cram that much information in, even if you're able to like keep it in your brain for long enough to do decently on the exam, that's not a way to like keeping that information in your brain as an abiding part of your knowledge base. All right. So interacting with the material a little at a time every day, and then like having a normal ramp up to an exam, that's a much better strategy. So I'm trying to structure the course to like support that way of learning as much as possible. For lab next week, we are going to be working with model kits, which are essentially like tinker toys that will help remind us about how to draw good Lewis structures and think about the shapes of molecules. All right. Lewis structures are a part of the prerequisite class to this class, Chemistry 121. If you don't remember how to draw good Lewis structures, or it's been a long time since you've interacted with those, the lab next week will be a nice reminder. All right. So that's good. Because we're working with tinker toys in lab next week, we don't have to worry about appropriate lab attire like goggles or long pants or closed-toed shoes. But in general, in lab, we need to be wearing our goggles, we need to be wearing long pants, and we need to be wearing closed-toed shoes. It's not as big a deal in winter quarter because most of the time it's cold enough that people wear long pants and closed-toed shoes anyway. Fall and spring quarters, it's a much bigger problem when students like see the nice weather and they're wearing short shorts and like sandals. That's actually a really big safety hazard in the lab. So I'll be insistent that we wear long pants and closed-toed shoes and goggles the entire time that we're in the lab. Please remember that. All right. I'll remind you of that next week on Tuesday when we do our lab safety training as well. I think that's everything that I was supposed to cover for you guys for the entire first meeting. Let's check that by looking at our course schedule. A course intro, we did that. We looked at the syllabus and we learned how to submit assignments as PDF files and where everything is on the Canvas course. All right. So I think that we're done for today, which means we're going to early, not let out. We're going to start talking about chapter 11. That's much more fun. All right. There are also times when we're not going to be able to cover as much every day as I thought. So let's get ahead instead of like starting out on pace when we have plenty of extra time. Yes, as a matter of fact, I thought all the dates were updated in Canvas. So I'm trying to mask my extreme disappointment at losing 45 minutes of time that I already spent updating those. I will re-update them. So for every assignment, for every homework assignment, lab assignment, and reading quiz, there should be a due date in Canvas associated with that. And that's really important because then you can use your Canvas calendar as like the reminder, right? It'll give you a notification. Hey, you got an assignment due tomorrow. Have you worked on that yet? Like I wish I'd had that when I was in school. So since I think it's a really good tool, I'll keep those deadlines updated. All right. I don't know where they went, and that's bothersome to me. Right.
Yeah, you go again. Yeah, exactly. Third time's a charm is what it's gonna be.
So chapter 11 is really the first chapter that organic chemistry is talked about in the textbook at all. This textbook is also an introduction to just general chemistry as well. So the first 9 chapters are really that introduction. Chapter 10 is something called nuclear chemistry, which for most undergraduates isn't very useful at all. Other people would disagree with that. And then we start organic chemistry in chapter 11. So I don't know if all of you understand what organic chemistry actually means. Does anybody know what that denotes when we talk about organic chemistry specifically?
Carbon based. This is all chemistry with carbon, is that? sort of right?
Sure.
Well, somebody else.
No, I think that's a pretty good definition. So more specifically, any carbon-containing molecules that are covalent compounds, which means that they have to have bonds between nonmetals. All right, that's something from the first quarter. So anytime we have bonds between atoms that are both nonmetals, we call those things covalent bonds, electrons being shared. So any molecules that have covalent bonds in them and contain carbon, we call those organic molecules. Chemists used to split hairs a little bit more on definitions, but really it's academic. All right, it's not important. So why is it that we have an entire introductory course that half of it is just about carbon when there are so many elements on the periodic table? What makes carbon so special? Anybody know?
Is it, I think it's because it's the only thing that sustains human life.
Yeah, I mean, most of our biological molecules have carbon at their core. All right, there are some exceptions to that. I mean, water is a really important biological molecule and it just has oxygen and hydrogen in it. But as we learn about our classes of biological molecules, most of you will have had a biology class at some point and know about those classes already. So what in the biggies, the biological molecules that we talk about are the nucleic acids. All right, so DNA and RNA are the nucleic acids, and then proteins and carbohydrates and lipids, the 4 big classes of biological molecules. All of those at their core are carbon-based molecules. They're all organic. So is it possible that somewhere else in the universe, life has evolved that doesn't have carbon involved with it at all? You think it is? I honestly don't know. And the reason why I don't know if it's possible is because carbon is really unique in terms of its ability to bond to other atoms in lots of different ways. The chemistry of carbon as an element is richer than the chemistry of any other element. In terms of the known reactions for how carbon can bond to other things, we know literally thousands of different chemical reactions that have to do with how carbon alone bonds to other things. That's why you can get a PhD in just organic chemistry. All right, you can study just the chemistry of carbon and what it does with other atoms. And that is a rich enough chemistry that they can give you a doctorate for. And even then, there can still be a lot of reactions of carbon-containing compounds that you probably don't know. There are tons. So it's an incredibly rich science, just learning about how carbon bonds to other atoms. We're just going to scratch the surface of that in this class. But that's why organic chemistry is important, all right? For one, carbon has a really rich chemistry all by itself. And two, carbon shows up in all life molecules, all the molecules that we know that sustain life, all right? Now, is it possible that somewhere else in the universe, a completely different paradigm has developed? Well, I think that we're probably working with the same palette, in other words, the same elements. There's probably nowhere else in the universe that the periodic table is different than it is here. So if we start with that as a presupposition, we would have to think about other elements that could have a rich enough chemistry to sustain life. If we were thinking about a possible substitute for carbon, something else that we could use that might replace carbon as the central atom in life molecules, what would our best bet be? So think carefully about what we know about the periodic table. This is actually like a coy way of me reminding you about some things from Chemistry 121. If we were thinking about an atom that would behave as similarly to carbon as possible, where would we look on the periodic table? Not just near carbon, above or below carbon on the periodic table. So our first principles from general chemistry tell us that atoms that are in the same group, the same vertical column on the periodic table, tend to behave similarly to one another. So if I was thinking about somewhere else in the universe, something else, another element replacing carbon, silicon would be the first place that I would look. Yeah, it's because it's right below carbon. And the elements in the same vertical columns tend to behave in similar ways. Now, practically, as a chemist, knowing some of the chemistry of silicon, a lot of the things that carbon can do, silicon can't. So, silicon probably isn't a great candidate, even though it shares many of the same properties as carbon. So I honestly don't know if we can escape carbon as the central biological atom. I don't know if it's possible. It'd be really cool if it was possible, but I don't know. Maybe we'll get the answer to that at some point. All right, probably not during my lifetime because we're not built for interstellar travel yet. We haven't figured that out. Maybe sometime. Hopefully we won't destroy the planet before we're prepared to leave. So if we're talking about the chemistry of carbon-containing compounds, the first thing that we have to do is understand how carbon bonds to other atoms. All right? If we remember anything about carbon from Chemistry 121, it is a group 4 element out of the main group elements. So what does carbon being in group 4 mean for how carbon is likely to behave? That means that carbon has 4 valence electrons. So those are electrons that carbon uses to form bonds to other atoms. That also tends to mean that carbon, when it forms stable organic compounds, it tends to have 4 total bonds. Now, 4 bonds can mean different things. One way that carbon could have 4 bonds is for carbon to have 4 total single bonds. A great example of that is probably the simplest organic molecule, All right, so I've drawn a Lewis structure of that simple organic molecule. We'll learn about how to name hydrocarbons like this as part of this class. But this molecule is methane, the primary component of cow farts and cow burps. It is also a very, very potent greenhouse gas. So the fact that we host enough livestock to feed and provide dairy for our world population, that actually does have a tremendous impact on our climate, because every one of those cows and every one of the other ruminants that we have on farms, they burp and fart lots and lots of methane because of how they process grass. That's not the only way for carbon to exist. Couldn't carbon also have 4 bonds by having a double bond and 2 single bonds? Absolutely. So here is a classic example of a molecule like that. A molecule with a double bond between carbon and oxygen, and then 2 single bonds from carbon to hydrogens. This molecule is formaldehyde. That's a common name for that molecule, but it's the one that people use the most often. What do we use formaldehyde for? What's that?
Preserving bodies?
Yeah. Cadavers. So we don't actually use formaldehyde all by itself, because formaldehyde at room temperature is a gas, but formaldehyde dissolves really well in water. So a solution of formaldehyde in water, that's what we embalm dead people with. All right. The reason why is because formaldehyde is so reactive that it basically kills anything alive that's around it. So that's a good way to keep things sterile.
Is that why we embalm people with that? So
Yeah.
it doesn't get to.
So the people don't rot. Formaldehyde doesn't last forever, but we don't really care if the people rot after they're buried. We just have to like hold them on for a little while before we can get rid of them. Yeah, that's what formaldehyde is for. It preserves things. If you use a solution of formaldehyde in a jar and throw tissue into it, bacteria can never grow on that tissue. The formaldehyde soaks through and kills all the bacteria on that surface. And then you have a completely sterile piece of tissue, which will never degrade.
So I've heard you're supposed to like wash when you buy new bed sheets because it has formaldehyde on it. But probably because.
I would highly doubt that.
I'm gonna Google it.
I would highly doubt
Let me
that.
check
It may be
this.
other things, but probably not formaldehyde. The reason why is because lots of people have pretty severe formaldehyde sensitivity or allergy.
If you use like, if you put like something edible to preserve it, would you like, if it like soaks in, would you be ingesting formaldehyde? Like to use it for like food preservatives?
No. Formaldehyde's really toxic. Yeah,
Okay.
we would never want that anywhere near our food.
Yeah.
To use it in clothing, actually, even though it is bad, to increase the wrinkle and crease resistance.
I would bet that the formaldehyde on clothing is probably gone mostly long before anybody actually wears it. Yeah, formaldehyde itself, remember, it's also a gas at room temperature. So even if you soak a piece of clothing in a solution of formaldehyde, if you just let it sit out for a while and the water leaves, the formaldehyde is mostly going to evaporate away.
A question that's kind of getting into the weeds, but when you have a cadaver or something, is it? It's a liquid, it's soluble in water, so they have, is it intravenous, like you would?
Yeah, I think that's the way they do it.
Okay.
Yeah, they pump people full of it through their veins.
So you use your like existing system that is well, actually.
Yeah, I mean, you have that system, why not make use of it, right?
Fast.
Plus, it's a lot more efficient than actually like throwing somebody into a tub of formaldehyde. That'd be a big tub. It takes a lot more formaldehyde solution to do that. This is still not the only way that we can end up with 4 total bonds. We could also have a situation where a carbon has 2 double bonds. Classic example of that. And if these drawings are making you twitch, that means you probably remember something from Chemistry 121. I'm drawing these in an intentionally crappy way. All right, we'll fix it in just a second. If they are not making you twitch, then you'll understand why they should make you twitch very soon. So here is an example of a molecule that has double bonds to carbon. That's CO2, most prevalent greenhouse gas. That's still not the only way that, or the last way that carbon can have 4 bonds. We can also have a triple bond and a single bond. Here's a classic example of that. That is hydrogen cyanide. Nasty stuff. Smells like bitter almonds. Deadly, deadly toxic. It's a gas. Also really useful for organic chemistry. There are lots of chemical reactions that we use hydrogen cyanide for.
How come N is stable?
But that is not the correct Lewis structure. There, much better. That would be an exception to the octet rule for nitrogen. Apologies, I was just drawing and not thinking. Thank you for the check. So the reason why I've written each one of these is to remind us about the ways that carbon can have its electrons around it. All right. One of the things that organic chemists think a lot about are the shapes of molecules. Matter of fact, we spend a lot of time talking about that in Chemistry 121. Particularly what we talk about when we talk about the shape of a molecule isn't the shape of a molecule as a whole, but just what the shape looks like around one central atom. All right, so let's remind ourselves about what the shapes around carbon look like in each of these different ways that we might see carbon. If we have carbon with 4 single bonds, do you guys remember how we predict the shapes of molecules based on how many places around the central atom where there are electrons? All right, if you don't remember the language, then that's okay. I'll remind you of it. We call the places around a central atom where there are electrons electron groups. Some other books sometimes refer to these as electron domains, but it means the same thing. All right. Electron groups are just the places around a central atom where one or more pairs of electrons exist. So whether we're talking about a single bond or a double bond or a triple bond or an unshared pair of electrons, any one of those things counts as one electron group. So when we look at methane up here, there are 4 total electron groups around carbon. Each one of those shared pairs of electrons is an electron group. So when we think about what the shape around carbon is in methane, the theory that we use, you don't have to remember this, but it's a really cool name, so I'm going to remind you of it. All right. The theory that we use to assign shapes to molecules is something called VSEPR theory, VSEPR. All right. What that stands for is valence shell electron pair repulsion. Sounds like real rocket science stuff. It's not hard at all. All right. In reality, what VSEPR theory tells us is that electrons repel other electrons. That's pretty simple. Negatively charged stuff repels other negatively charged stuff. So what this means for us is that in order to predict the shapes around a central atom, we have to put the electron groups as far apart from one another as they possibly can around the central atom. Now, what does that look like for something with maybe let's go in reverse and make it as easy as possible. Let's start with these two. And the reason why we're going to start with those two is because each of them only has 2 electron groups on carbon. Does that make sense? So if we want to put 2 electron groups as far apart from one another as they can possibly be around that central carbon, what's the farthest apart that they can be from one another?
Opposite sides.
On opposite sides, right? Doesn't that make sense? So the way that we define that is something called a bond angle, an angle between those 2 bonds. And the bond angle for things that are on opposite sides would be what? 180 degrees apart from one another. So that is the real shape around carbon for any carbon that has just 2 electron groups. And that could be a couple of double bonds, or it could be a single bond and a triple bond, or a triple bond and a single bond. All right. Either of those ways of thinking about carbon means that that carbon has 2 electron groups. And anytime a carbon has just 2 electron groups, that means that those groups are going to be 180 degrees apart from one another. So with 180-degree bond angles, the shape that we talk about for a carbon like this, we call the shape around that carbon linear, because those 3 atoms end up in a straight line. That would be the same if we were talking about a triple bond and a single bond. The shape around that central carbon is also linear, 180-degree bond angles. Let's think about what a carbon would look like that had 3 electron groups. So formaldehyde is a good example of that. Even here, you can see that I have not placed those 3 electron groups as far apart as they possibly can be from one another. So if I was predicting the bond angle from this picture, which is perfectly fine Lewis structure of formaldehyde, I might predict that that angle was only 90 degrees, but that's not as far apart as those things can be from one another around that central carbon. If I was doing a better job at drawing those electron groups as far apart from one another as they could be, then the picture would probably look something more like this. What would our bond angles look like for something where we had 3 electron groups? What's the farthest apart that those bonds can be from one another? Yeah, so think about it this way. Like if this was a complete circle, 360 degrees around carbon, the distance between these bonds is 1/3 of the way around that circle. So we predict bond angles of 120 degrees for a carbon that has 3 electron groups. Now, what do we call this shape around carbon? All right, this is a little harder to remember, but if we think about these atoms, all of them are in the same XY plane. None of them are sticking out toward us or going back into the paper. And those 4 atoms form the rough shape of a triangle. So we call this shape trigonal planar. So linear is a possible shape around carbon. Trigonal planar is a possible shape around carbon for carbons that have 3 electron groups. The last one we have to talk about is the first one that I drew, methane, or any carbon that has 4 electron groups. 4 electron groups is a big step up in difficulty. And the reason why is because once we get to 4 electron groups, the molecule isn't just 2-dimensional anymore. We have to think in 3 dimensions to get those 4 electron groups as far apart from one another as they possibly can. What's really weird, have any of you guys had physics with Brian Manning? Anybody? No? Okay, well, Brian Manning, our physics professor on campus here, like literally stopped by my office like a half hour before this class and asked me, why is water bent? Why is the bond angle between the hydrogens not 180 degrees? And that's like exactly what we're discussing right now, Vesper theory. All right. So I got to go through Vesper theory with him and he was excited about it. And now I get to share it with you guys. Water is actually the same idea that we're looking at right here. And we'll talk about why in just a second. We'll look at carbon first though, all right, and methane. So if we want to get those 4 electron groups in methane as far apart from one another as possible, it is not a case where the bond angles are 90 degrees. That's thinking 2-dimensionally. In reality, we can get those bonds even farther apart from one another if the first 2 bonds are in the same plane as the board, but then we have another bond to hydrogen that is sort of like projecting out toward us. By convention, chemists, when they project a bond out toward somebody or out in front of the board that they're drawing on, they represent that with a wedge. Likewise, by convention, when chemists talk about a bond that is pointing away from them, they use dashes to represent that. So this is a more 3-dimensional representation of what methane looks like. The bond angles are not 90 degrees. They're a little bigger than that. As a matter of fact, I actually have not gotten a perfect answer from any of our math department yet, but we sometimes ask odd questions, like Brian asked me, like, why is water bent? All right. And a question I've not gotten an answer for from our mathematicians yet, but we should be able to actually predict this bond angle by just thinking about placing a point mass, doesn't have to be carbon, just a point mass in the center, and then having 4 rays that point out at angles that are as far apart from one another as possible. We should be able to derive geometrically what that bond angle is. All right. I don't know how to derive that bond angle geometrically, but I do know what the bond angle is because I just memorized it. So the bond angle for something with 4 electron groups, the farthest apart those 4 electron groups can be, it's not a nice, easy number. It's 109.5 degrees. It's really important for us to think back through this idea of the shapes around carbon, because for the first half of the class, we look at nothing but carbon-containing molecules, all right? And those are the shapes that we might see in any organic molecule. Carbon is either going to have 2 or 3 or 4 electron groups. When you get to a majors level organic chemistry class, there are times when carbon, at least for a little while, behaves kind of strangely. All right, let me show you an example of what that might look like, even though we won't see any molecules like that in this class. What if we had a carbon that looked like this? A carbon with just 3 bonds and a positive 1 charge on it. We call that kind of carbon a carbocation. You won't see those in this class. It's a majors thing. We could still predict the shape around this carbon. How many electron groups are there on that carbon?
3.
There are not 4. That is not a pair of electrons. Yeah, that's not a pair of electrons. All that tells us is that the carbon has a +1 charge. There are 3 electron groups on that carbon. What are the bond angles there?
120.
120. What's the shape around that carbon? Trigonal planar. I think there are actually books that call it triangular planar, but trigonal planar is more common. All right. Yeah. I just want you to seem like the smartest person. It actually may be it may be a smarter thing to say triagonal planar instead, because there aren't as many books that say that. So that means that you've read all of them. I don't know. I don't know.
You made your own call.
The other thing that we'll talk about as we go through this chapter and the chapters to come, there are a lot of these things called functional groups. That's one of the main things that we learn, is the behavior of different functional groups, parts of an organic molecule that have predictable behaviors. All right. You've probably heard of some of these before, like alcohols, for example. All right. So ethanol, the stuff that's in booze, is one example of a molecule that has an alcohol functional group in it. The reason why we worry about functional groups is because it allows us to predict the behavior of molecules in reactions. In other words, if I know how one alcohol reacts then I probably know something about how all other alcohols are going to behave in the same kinds of reactions. All right, they're predictable ways of categorizing the reactions in organic chemistry. So another of the things that we have to learn in chapter 11 is some of those functional groups. All right, some of those things, the pieces that we look at in an organic molecule that tell us how it's going to behave. That's probably better than a book definition for functional groups. And I have to look in chapter 11 to make sure that I don't leave out any of the functional groups or that I don't put in some that we don't cover in this class, because it's both things are true. Okay,
Wait, what is that? And so the one where it pops out is called what?
yeah, oh, we didn't talk about the shape. Okay, I'm sorry.
No, that's okay. I just was like,
Yeah, so the shape where we have 4 electron groups on the central atom is a hard one to name. You have to use your imagination. So imagine this is a 3-dimensional figure. So take any 3 hydrogens that you want to and make those 3 hydrogens form a side of that 3-dimensional figure. How many sides would that figure have then? All right, maybe we can't just see it, so I'll draw it in instead. All right, so I'll have to redraw this afterward because I'm going to ruin it by what I'm about to do right here. But imagine those 3 hydrogens form a side of a figure. And this hydrogen and this hydrogen and this hydrogen form another side of the figure. And then those back 3 hydrogens form a side of the figure. And then the bottom 3 hydrogens form a side of the figure. How many sides? 4 sides. So in 3 dimensions, this looks like a 4-sided figure where all of the sides are exactly the same size. And in geometry, we call that shape a tetrahedron. So that's where we get this name from. We call this shape where a central atom has 4 electron groups. We call it tetrahedral, which literally means 4-sided. Now I'm going to redraw that because I can't stand for it not to look the way that it's supposed to. You do not have to draw your Lewis structures for organic molecules to look like this all the time. This is a Lewis structure, but it's a particular Lewis structure that allows us to look at the shape around that carbon more easily. There's nothing wrong with drawing methane like this. That is a correct Lewis structure for methane. We just have to understand that Lewis structures don't always do a good job of predicting the shapes of molecules. Instead, when we predict the shape around a carbon, we have to look at how many electron groups it has. That's what allows us to predict the shape correctly. Now, that being said, when it is easy for us to draw an organic molecule or a part of an organic molecule and show the correct shape, we should do that. Which is why it should make you cringe a little bit anytime somebody draws CO2 and it looks like this. All right. Is that a correct Lewis structure? Yes. Does that Lewis structure do us any favors in showing the correct shape of CO2? No. And we don't even have to worry about drawing it in 3 dimensions to have our Lewis structure correctly indicate the shape. So I don't ever draw my CO2 like this. I always draw it like this because I know that that bond angle is 180 degrees. So why not show that if I don't even have to worry about 3 dimensions to make that happen? Whenever I draw a part of a molecule that has 3 electron groups in it, I try and put those 3 electron groups about 120 degrees apart. It doesn't cost me anything to do that in my Lewis structure. And I've done myself a favor because I can immediately look at that. And that is what the shape looks like. We just don't do that with 4 electron groups because it can get really complex really quickly. Is everybody good on the shapes around carbon that we're likely to encounter? All right. So now that we've done those shapes for carbon, I want to talk for just a second before we get to functional groups, and we may not even have time to get to them because we've got like 10 minutes left today. All right. If we look at water, Oxygen on the periodic table is in group 6, which means it has 6 valence electrons. Hydrogen in group 1 has 1 valence electron, which means that in total, H2O should have 8 electrons represented in its Lewis structure. So if I give each of the hydrogens the pair of electrons that they need, and then I put the 4 remaining electrons on oxygen, that is a good-looking Lewis structure for water. But it does not do us any favors in correctly indicating the shape around oxygen in water. The reason why is because there are 4 electron groups on that central oxygen. Those unshared pairs of electrons, we often call those lone pairs, all right? Those lone pairs each count as an electron group as well. So the oxygen in water, just like the carbon in methane, has 4 electron groups on it. Anytime we think about something with 4 electron groups, that bond angle in our heads, the weird one, 109.5, that should be our reference point for what we think about for bond angles anytime we see something with 4 electron groups. So the real shape of water is not linear. A better way to describe that shape, God, I'm gonna draw it far enough away so that we don't have like polluting electrons from another molecule. And I'm going to use the about symbol here. But because there are 4 electron groups on water, we can't say that this oxygen has a linear shape because those 2 hydrogens are not 180 degrees apart. And if it's not linear, then what do we call it instead? We can't call it tetrahedral because these aren't bonds to other atoms. Yeah, this is bent. So when we just have that central atom bound to 2 other atoms, our only options for the shape that we can get is either linear if those 3 atoms are in a straight line, or bent if they're not in a straight line. So in this case, they're not in a straight line. So the shape around that oxygen is bent. Bent. We do. We have 2 hours today.
Yeah,
Yeah.
every day, every
Every
time,
day.
every time. Yeah.
That makes me so happy. I love that.
That'd be terrible.
We're not going to go until 1:50 because we didn't take a break at the hour, and going for an hour and 50 minutes, like you guys will literally be puddles by the end. Maybe not today because it's like a light day, but on a regular class day, we would be puddles with an hour and 50 minutes of organic chemistry straight. So we'll try to either take a 5 or 10 minute break in the middle or let out early. So we'll try and go until like maybe 1:30 or a little after, and then I'll let you guys go. All right. So we do have enough time to talk about functional groups today, which makes me really happy. Okay. So a non-book definition for what functional groups might look like. What does functional mean? Like outside the world of chemistry. Functional. It does something. It has a function, right? These functional groups fit that definition very well. Those functional groups do something. They have a behavior or a function. All right. So these are parts of an organic molecule that have predictable behaviors or predictable functions. An alkane isn't really much of a functional group, but more like what we call molecules that don't have any functional groups at all. So alkanes have nothing but carbon-hydrogen single bonds or carbon-carbon single bonds in them. So I'm giving you a couple of examples of those. The first one of those that I'm drawing for you is methane. The second one is Hank Hill's favorite molecule. Anybody know what one that is?
Propane.
Very good. Propane.
Right, you said that they only have,
I'm writing it down too. So alkanes contain only carbon, hydrogen, and carbon-carbon single bonds, nothing else. And even though alkanes do have functions, they do have predictable behaviors, the number of things that we can actually do to them using chemistry is really, really small. We can't do much to alkanes. They are not very reactive. All right. But they do have like a couple of chemical reactions. And we'll even learn one of those in this class. Now note the change in suffix for this second class of organic molecules. Alkenes contain a carbon-carbon double bond. And carbon-carbon double bonds have lots and lots of functions. They are one of the most important functional groups in organic chemistry. We can take an alkene and turn it into almost any other functional group in like one step. Are we going to learn all of those reactions in this class? Hell no. It's a lot, hundreds of reactions of alkenes. So an example of that might be a molecule like this. I'm going to name it for us as well. This molecule is propene. Notice how similar that molecule is to propane. Propane is an alkane with 3 carbons in it. The 3-carbon alkene has the same prefix, so that prop has something to do with the number 3 in terms of carbons, but our suffix "ene" tells us that there's a carbon-carbon double bond in there someplace. All right, so we're starting to hint at nomenclature, how to name organic molecules a little bit by learning about these functional groups. If we change that suffix from "ene" to "ine," Y-N-E, we have an alkyne. Alkynes contain carbon-carbon triple bonds. So what I want you guys to do is just try to draw a good Lewis structure for the molecule propyne now. Propyne. What might that look like? We know that it's going to have 3 total carbons in it. And we know that there's going to be a carbon-carbon triple bond in there. All right. So we know that we have a 3-carbon molecule that contains a carbon-carbon triple bond. Would it matter whether we drew it like this or like this? That's another thing that we'll have to learn, is that sometimes molecules that look different actually aren't different. They're just like rotated. So let's think about this. We know that these molecules have to have some hydrogens in them as well. How do we know how many hydrogens we would expect in this molecule? Well, we have to have an octet for each one of our carbons. In other words, each of our carbons has to have 4 total bonds. So how many hydrogens would we expect there to be on this carbon?
3.
3, because there's only 1 bond shown right now. How many hydrogens would we expect to be on that carbon?
None.
None, because there are already 4 bonds. And then finally, how many hydrogens on that last carbon?
1.
Only 1, because there are 3 bonds shown already. Now we can do the same thing over here. It's just we flip which side. Those 2 molecules, even though they look a little different, all we've done is like flip that thing over like a pancake. It's the same molecule. Either one of those is propene. Now, we will also work on being able to draw these molecules without drawing out the entire Lewis structure, because organic chemists would spend all their time drawing Lewis structures if they didn't have an effective way to shorthand them. So, just as a preview, this is what this molecule will look like in the way that we actually draw them as professional organic chemists, which I will teach you. It's called bond line drawing. All right. This is what the bond line drawing looks like for propine.
Is there a dot in between?
There doesn't have to be.
Oh.
This is what the bond line drawing looks like for propene. This is what the bond line drawing looks like for propane. We will talk more about how we get from a Lewis structure to a bond line drawing next time that we're together, not today. I just want to give you a preview. All right, what do we not show on our bond line drawing? What aren't there any of in that bond line drawing? Hydrogens, right? We have to be able to tell how many hydrogens there are on each of those carbons from that picture. So what I want you to start thinking about in your head is, how do we know? How do we know how many hydrogens to expect on each one of those carbons? All right, if that makes you curious, you can watch the topical videos, figure that out for our next class. Okay. These are a set of functional groups that have a single bond between carbon and a heteroatom. The prefix hetero means opposite or other. All right. So heteroatom means an atom that's not carbon or hydrogen. Here is just one example of a functional group called an alkyl halide. And that means that that carbon has to have, or a carbon in that molecule has to have a single bond to some halogen. It could be fluorine or chlorine or bromine or iodine. All right, we don't normally think about astatine because it's radioactive anyway. Nobody uses it. Acetine's right below iodine, periodically. So alkyl halides. It could be something bigger. Something like this. Notice how long it took me to draw that Lewis structure. That was drudgery. Do you know what I hate? Drudgery. So instead, we are going to draw this same thing using bond line drawing, and it'll take much, much less time. Now, depending on what book you're using or what you're doing with the molecule, the bond line drawing for this might look like this, or you might still show those unshared pairs of electrons on fluorine. Either way is perfectly fine. If we don't show them, we assume they're there anyway. Why? Because fluorine has to have an octet. It has to have 8 total electrons around it. Do you guys want to know the name of this stuff? All right, it's a little complex, but it's also going to give you a clue about how we name things. We call this 2-fluoro, 2-methyl propane. If you don't understand, duh, we haven't talked about it yet. All right, we'll get there. So anytime we have a hydrocarbon that has a carbon halogen bond in it, we call that kind of functional group, the halogen itself, an alkyl halide. All right. So alkyl halides have lots of really important, interesting chemistry associated with them. Here's an example of an alkyl halide you guys have heard of before. Now, the common name for this stuff is a name that you've heard of. If we were talking about the systematic name for it, this would be trichloromethane. Don't worry about that. All right. We'll have plenty of time to name stuff. You've heard of the common name of this before. No. It's actually a really good solvent for lots and lots of organic chemistry reactions, but it's more expensive and harder to get because some people use it in stupid ways. Yeah.
What is the first one of the alcohol halides you wrote up there? What is that called?
That would just be chloromethane. And I didn't even draw in the, shame on me. I didn't draw the lone pairs in on that chlorine, shame on me. All right. We don't have to name everything, we'll get there, all right? So I just want you to be able to recognize that anytime we have a hydrocarbon that has a halogen bound to carbon someplace in it, that's an alkyl halide, all right? Anytime we have a hydrocarbon, and I'm going to start using this general notation as well. Anytime we have an R group, so R just means like any hydrocarbon that you can think of, any carbon chain that you can think of. And that carbon chain has a bond to an OH group. We call that an alcohol. Alcohols are very, very useful functional groups. So the classic example of such an alcohol is the stuff in booze. A 2-carbon long alcohol. Ethanol. But the key feature is a carbon with a bond to OH. Notice I'm already shorthanding without even meaning to do that. There is a covalent bond between oxygen and hydrogen there. All right. Organic chemists hate drawing out all their Lewis structures. Any hydrocarbon. It's a placeholder for any hydrocarbon. So instead of a 2-carbon chain, it could be a 20-carbon chain. All right. Instead of a straight chain, it could be a bunch of branches of the hydrocarbon. So R is just a general term for like any hydrocarbon that you attach to it. We're running out of time, so we'll try and get through the rest of these. So if we have 2 hydrocarbon chains that are each bound to a central oxygen, we call that functional group an ether. Where have you heard the term ether before? Thor? That's different. That's metaphysical ether. All right.
Still say
okay.
no.
There is actually like
Still
a
have.
physical term for ether. Well, the metaphysical ethers, because it's like vapory, right? So most ethers are, at least small ones, have very low boiling temperatures, which means they turn into gases easily.
Is it like a,
Yes, as an anesthetic. So the earliest ethers that were used as anesthetics were probably diethyl ether. It's also, so diethyl, meaning that there is a 2-carbon chain on each side of that central oxygen. So that's an example of an ether. The key here is that we have a hydrocarbon on each side bound to a central oxygen. That's what makes an ether. Right? Those used to be used as anesthesia, but they're pretty unsafe. If you give somebody the wrong dose of diethyl ether, their heart just stops and they die. Now we use halogenated ethers as the things that are inhaled for surgery anesthetics, more controllable and dosable. So a little bit safer. You can still kill somebody by giving too much anesthesia, which is why anesthesiologists make lots and lots of money, because they have to sign on the dotted line. They're responsible if they muff it up. The next one of these is going to be a little harder, because an amine functional group can look like a few different things. We can have a hydrocarbon attached to nitrogen, and that nitrogen can also have 2 hydrogens bound to it. Or we could have 2 different or 2 identical hydrocarbons bound to a nitrogen and 1 hydrogen bound to that nitrogen. Or we could have 3 different hydrocarbons or 3 of the same hydrocarbon attached to a central nitrogen. Any one of those is an amine. So the key for an amine functional group is we have some sort of bond between nitrogen and carbon, and it can be 1 carbon or 2 carbons or 3 carbons. Anybody know anything about the amine functional group? Anybody know what amines smell like? It's not super pleasant. The amines that most of you have probably smelled before were what you smelled if you smelled fish that had been sitting out at room temperature for too long. All right. So fish that sits out at room temperature, when it decomposes, it produces amines. And what do they smell like? They smell like rotting fish. If you go to a fish market and you smell amines, probably shouldn't buy fish at that fish market. That means they didn't keep their fish cold enough or they kept it out for too long. Fresh fish should have a pleasant smell, like a slightly sweet smell. Yeah, if you smell amines at your fish market, they kept their fish out too long or not cold enough. The next and last one of our compounds with a single bond between carbon and a heteroatom is something called a thiol. A thiol looks very much like an alcohol. All right. And again, I'm not drawing Lewis structures very well here. If I was talking about a thiol and drawing out all the bonds, I would have a single bond between sulfur and hydrogen. We just know that that bond has to be there so that we shorten our molecule up a little bit by drawing the functional group this way. So this could be any hydrocarbon. All right. Let me show you one example of a thiol. A 4-carbon thiol, if I were naming this, that is just marker. I don't know what that is. It's scrubbing it. A 4-carbon thiol. We would name this butane thiol. Incredibly smelly stuff. Butane thiol is one of the primary smell components of skunk spray. Thiols are stanky. They all smell like skunk. Our noses are very sensitive to that, and that's actually a good thing. Other small thiols are added at very, very low concentrations to natural gas. Why? Because they burn very cleanly and they allow us to smell very sensitively if there is a gas leak in our household. So if you smell something that smells kind of skunky in your house, you may have a gas leak. So get out and call the gas company. Wow, that took me a long time to draw that Lewis structure. If I was drawing the bond line version of it, all done. You see why we use those bond line drawings instead of Lewis structures? We don't lose any information. We get all of that, but we only have to draw that instead. All right, we'll practice more with bond line drawings next time that we're together. We also have some more functional groups to talk about, but legit, we were supposed to cover none of chapter 11 today, and we got like half of it done. So I'll call that a big win for us.
Tomorrow we have class. Is that-
That's what I meant. Yeah,
Oh,
tomorrow class. It's going to take me a little while to get used to having a Thursday, Friday class. Originally, we were slated to have class on Tuesdays and Thursdays, or sorry, Tuesdays and Fridays and a lab on Thursdays. Or I was going to make it Tuesday, Thursday class and Friday lab. But for like space reasons, we ended up having to do our lab on Tuesdays. All right, so yeah, we meet again tomorrow.
Do we have any homework for tomorrow? Just because the due dates are.
No homework for tomorrow.
Okay, great.
No homework for tomorrow.
Thank you.
I'll see you guys tomorrow. It's so good to have met all of you. Can I please pick up those name tags? Because I will try and hand them back to you. That will be my mechanism for learning your names quickly. Yeah. Some of those aren't even mine. All of them. It's gonna be a problem. Let's figure out.
Okay, I did put my last name. Perfect. Okay.
Becca, when did I have you in class? It's been a while, right?
What?
When did I have you in class?
Like, that's, I would say like a year ago, I think.
A year ago? Okay.
Almost exactly.
I've emailed you about borrowing the book.
You did.
Yes,
Okay.
thank you so much.
What do you got? Like, what do you prefer to be called?
Okay, that's okay. I'm okay with that.
I have a literal question for you.
All right,
So.
thanks, Teresa. Are you done? Are you still there? I'm sorry.
No, but that's also fine. So